not q, and you have to prove a case that contradicts that.
All right. We are going to finish up this chapter on induction. And then next time we're going to start with the next chapter. So I guess that's chapter 5. I start forgetting what chapter we're on. Okay. But so some of the proofs today are ones that take a little bit of creative problem solving and a little, like, I often tell my students that a good mathematician is a good mathematician. You have to have a little bag of tricks. And so a lot of these proofs today, you kind of have to reach into your bag of tricks. So some of these are just take a little bit of creativity. All right, so let's try them out and see what I'm talking about. Okay, so we are still doing proof by induction. So this one, we want to prove that for any, and we're assuming integer. Okay, n greater than or equal to 2, that 3 to the n is greater than 2 to the n plus n squared. Okay, so we know that if we're going to, like, let's just go ahead and say we use a proof by induction. Okay. All right, and where do we start every proof by induction? I don't know. I only know how to do proof by contradiction and proof by contrapositive and proof by cases because that's all I've been thinking about. Okay, anybody remember where we start proof by induction? Yes, the base case. Good. Okay, so we'll start with the base case. Okay, and what is our base case? N equals 2. So the smallest value of n that we should ever consider. And since we're trying to prove it for n is greater than or equal to 2, our starting point is going to be at 2. And then we'll have to prove from there on. Okay, so our base case is the smallest possible n value of 2. Okay. So our base case is when n equals 2. All right, and so what we want to do is we want to basically verify that the left side of the inequality is actually greater than the right side of the inequality. So let's look at, okay. All right, so let me put a little, when n equals 2, the left side, 3 to the n, will be 3 squared, which is 9. And the right side of the inequality, the 2n plus n squared, okay, if n is 2, that's going to be 2 squared plus, and then 2 squared again. So that's 4 plus 4 is 8. Okay, so the left side, 9, is indeed greater than 8. Okay, so since 9 is greater than 8, okay, it is true for n equals 2. All right, so we've established that it's true for the base case. Okay, and so the next thing we need to do is our inductive step. Okay. So what is the key thing that we need to do in our inductive step? All right, what is it, Vaughn?
Prove that if the theorem is true for the base case, then the theorem is true for the base case plus 1.
Okay, if the theorem is true for an arbitrary k, then it's true for that arbitrary k plus 1. Yes, the base case will get it started, but we don't want to tie it to the base case. We want to make it an arbitrary. Good. Okay, so we're going to assume that what we're trying to prove is true for some arbitrary k that's bigger than or equal to n. So this is what we're trying to prove, and we want to say, okay, we're going to assume that 3 to the k is greater than 2 to the k plus k squared for some integer k where k has to be greater than or equal to 2. Okay, and then, like Vaughn says, then we will show that if this is true, then we can show that it will be true for the one after k. So that 3 to the k plus 1 will have to be greater than 2 to the k plus 1 plus k plus 1 squared. Okay, so everywhere we saw a k before, we have to substitute a k plus 1 in. So again, remember, that doesn't mean that this is true. That just means that if this is true, then this k plus 1 case will also have to be true. Okay. So that's our goal. That's what we need to show. Okay, and so that means we need to think about this expression here, 3 to the k plus 1. And we know that we're going to have to somehow get this, let's call it our inductive hypothesis, this assumption here, that's going to have to be involved. Okay, so notice that's just 3 to the k. So if we can somehow rewrite this in terms of 3 to the k, then we can use some kind of then we can use this inductive hypothesis that we know, okay, that this is, or that we assume that 3 to the k is greater than that. Okay, so could we rewrite this in a way in terms of 3 to the k? How could we rewrite that in terms of 3 to the k? Not plus 3, times 3, yes, right. So that's like 3 times 3 to the k, right? Because if I have a common base, I would add these exponents when I multiply, and there's like an implied 1 here, so that would give me 3 to the k plus 1, right? All right, so I know that this is equal to 3 times 3 to the k, and now I have this 3 to the k. Okay, and so 3 to the k, so imagine if I have 3 to the k, it's greater than this. If I multiply both sides of this inequality by 3, then that inequality will stand. So I know that this has to be greater than 3 times 2 to the k plus k squared, as long as this is true. So this would be by the inductive hypothesis. Okay. So the only reason that we could get this inequality to be true is if this were true. Right? If this were true, then I could just multiply both sides by 3, and we would still have this inequality. Okay. And so on the left side, I have this 3k plus 1. And on the right side, I've got this expression. So I just somehow have to show that this thing right here is greater than that. Okay. So let's go ahead and start by multiplying. Well, let's go ahead and think about sometimes you have to work backwards a little bit. So imagine this thing right here. Okay. So this can just be in our little thought bubble. Okay, this is our side thinking. Okay, so this is 2 to the k plus 1, and if I expand this out, this is going to be k squared plus 2k plus 1. So I might want to have that, this thing and this thing are the same, but I might want to have that, okay, in my mind as a goal. All right, so notice if I am trying to get this thing to look kind of like this thing, there's a 2 to the k plus 1. Okay. Here I don't have it, I have a 2 to the k, but I don't have a 2 to the k plus 1. Okay. Now if I were to distribute this 3 through, I would have 3 times 2 to the k, but that doesn't really give me 2 to the k plus 1. What I really would like to get 2 to the k plus 1 is 2 times 2 to the k. Okay. So here's where my creative problem solving skills come in, and so let's say, well, let's rewrite 3 as 2 plus 1. Okay. So if I rewrite this 3 as 2 plus 1, okay, then look, when I FOIL this out, I have 2 times 2 to the k, and that'll give me the 2 to the k that I'm kind of wanting in my final answer, and that will be helpful. So let's do, so that if I expand that out, I'll have 2 to the k plus 1 when I multiply these two. And then I'll have a 2k squared, and then a 2 to the k, and then I'll have another k squared. Okay. So, again, I'll compare this to what I'm thinking on the side. Okay, I've got the 2 to the k plus 1, that matches. There's a k squared. Well, that matches this one. So maybe let's rearrange this. Okay, so this is just the same thing as 2 to the k plus 1. That matches. Let me move my k squared over here. So that matches. Let me just scooch everything down. So I have the 2k squared plus 2 to the k. So right now I have two things that match. And now I just have to think about the relationship between the other two things down here and this thing down here. Okay. So let's compare this one and this one. Okay. So, like, what do you feel? What's bigger, 2k squared or 2k? Yeah, usually 2k squared is bigger. I mean, I'm sure there's some instances in which it's not, but okay. Let's compare. So if I look at 2k squared and figure out when that will be bigger than 2k, we could divide both sides by 2. Okay, we know that k is a positive number. We don't have to worry about dividing by 0 or a negative number that flips the sign or anything. So this is true when, okay, k is greater than 1. Okay, divide both sides by 2, divide both sides by k, and you get k is greater than 1. Okay, we know k is greater than 1 because it's greater than or equal to 2. Okay, so I know that this term right here is bigger than that term right here. So if I add all this stuff together, it will definitely, okay, so this right here, 2 to the k plus 1 plus k squared plus 2k squared plus 2k has to be greater than 2k plus 1 plus k squared, and I'll replace that with just 2k. Okay. So I replaced this with something smaller, so this side has to be bigger than that side. And so 3k plus 1 is still greater than all of this because it was greater than this one. That's greater than that one. All right. So now we have this that matches. We have this that matches. We have this one that matches. And now we just have to think about these ones. Okay. So if I think about 2 to the k and 1, okay, well, when, like if we try to figure out when is 2 to the k bigger than 1? So could I replace this with a 1 and still have this one be bigger than when I replace it with a 1? So 2 to the k is going to be bigger to the 1 than when? When will 2 to the k be bigger than 1? When is it equal to 1? When k is 0. So when is it bigger than 1? When it's greater than 0. So that's true when k is greater than 0. Well, k is definitely greater than 0 because it's greater than or equal to 2. And so this part right here, 2 to the k plus 1 plus k squared plus 2k plus 2 to the k has to be greater than 2 to the k plus 1 plus k squared plus 2k plus 1. Okay, so I just replaced this with something that's smaller than it, so certainly this sum has to be larger than that sum. Okay. So when you string all this together, what you have is what we started with, 3 to the k plus 1 is greater than what we ended with over here, 2 to the k plus 1 plus k squared plus 2k plus 1. That's exactly what we wanted it to be greater than. Okay. Okay. I've sort of run out of room, so I have to write this small. Okay, but that's what we set off to show. I mean, this is, let's go ahead and put that this is equal to 2 to the k plus 1 times k plus 1 squared Okay. Even though we thought that on the side, we probably didn't include that in our proof. So let's go ahead and include it now. So we have this, 3 to the k plus 1 is greater than that, which is what we set out to prove. And so our last little statement should be, therefore, by the principle of mathematical induction, okay, 3 to the n has to be greater than 2 to the n plus n squared for all values of n greater than or equal to 2. Yes?
I'm a little confused with the line where you have by the inductive hypothesis. How do you get the part to the right of the...
Okay, so my inductive hypothesis is right here. Okay, so if I were to just multiply both sides of this inequality by 3, then I'd get this down here. So the only reason that this inequality is true is because I assumed that that inequality was true.
When you already know it's true, if you have an inequality that's true and you multiply both sides by the same thing, would it still be true?
Yes, exactly, exactly. Yep. So I know that this is, so as long as this inequality was true, if I multiply it by both sides by 3, the inequality is still true. So that's what I'm saying, that this inequality is true because I assumed that that one was true. That's right. See what I mean? How this takes a little bit of ingenuity and creative thinking and problem solving. So, okay. Any other questions? All right. The next one's a little bit easier. It's also an inequality. Like the inequality ones are like you have to kind of just, all right, can I just find this is bigger than this kind of, and so that's why you just need a little creativity. So next one, we'll see. Maybe I'll see if you can give me more ideas on this one. All right. So another inequality. So that for any n greater than or equal to 4, we want to show that n factorial is greater than or equal to 2. Okay, so we're going to use induction on n. Okay, so start with our base case. Our base case is the smallest possible value of n, so in this case it's 4. So when n equals 4, we want to look at what happens. So on the left side we have n factorial, so that'll be 4 factorial, which is 24. If you don't have that one memorized, I do. Okay, on the right side we have 2 to the n, so n is 4, that's going to be 2 to the 4th, that's 16. So indeed, the 24 on the left side will be greater than the 16. So since 24 is indeed greater than 16, okay, it is true for our base case of n equals 4. So now we need to consider our inductive step. So just like last time, we're going to assume that it's true for some value of k. That's 4 or bigger. Okay, so we're going to assume that what we're trying to prove, so with k, so k factorial is greater than or equal to 2 to the k for some integer k, k being greater than or equal to 4. And then we have to show that if that's true, then it's going to be true for the next k in line, for k plus 1. So we replace that k with k plus 1, so k plus 1 factorial will have to be greater than or equal to 2 to the k plus 1. So that's our goal. We need to show that k plus 1 factorial will be greater than or equal to 2 to the k plus 1. So we know it's all going to depend on this inductive hypothesis. The inductive hypothesis tells us something about k factorial. Okay, so if we look at the left-hand side of our inequality, which is k plus 1 factorial, the question is, can we rewrite that in terms of something that we know from our inductive hypothesis? So could I rewrite this in terms of k factorial? Good. So this is equal to k plus 1 times k factorial. Okay, so if you don't see that, let's write it out. So k plus 1 factorial, what does that mean? That means you start with k plus 1, okay, and then you multiply it by the number before it, which is k, times the number before it, which is k minus 1, times the number before it, k minus 2, and multiply this all until we get down to 1, right? But this right here, k times k minus 1 times k minus 2, that's just k factorial, right? So that's why this is equal to k plus 1 times k factorial. Very similar to pulling the last term off of a summation, but this is kind of like pulling the last term off of a product. Okay. So this puts us in a good spot because we know something about k factorial from our inductive hypothesis. Okay, so think about what we did last time. Okay, so if this were true, okay, what would I have to do to both sides of this to get this k plus 1 times k factorial on the left side? So what am I going to have to put on the right side? This is greater than or equal to what? True, but that's not going to help me get to, I mean, sure, if this one I can multiply it by something bigger, it'll still be, but that's not necessarily going to get me there. There's no way I'm going to get to the 2k plus 1 if I just have 2 to the k over here. So over here, I had k factorial. What did I have to multiply that by to get this side? Yeah, but times k plus 1. So if I introduce that same factor on the other side, now notice k is greater than or equal to 4, so I'm multiplying by a positive number. I won't have to switch the sign. I can still guarantee that that it will be k plus 1 larger than k plus 1 times 2 to the k, right? But the only reason that's true is because I'm assuming this is true. So if I start with this and I multiply both sides by k plus 1, that inequality will still be true. Okay, so this is true only because of the inductive hypothesis. If the inductive hypothesis weren't true, then we couldn't make that statement. Okay. And so now let's look at this. Okay, let's go ahead and distribute this through so that this is the same thing as k times 2 to the k plus 2 to the k. Now what I really would like, so if I look at this, 2 to the k plus 1, the way that I get that is multiplying 2 to the k by 2, right? So the question is, all right, if I were to replace this k with 2 so that I could get this term to look like that, okay, would that be okay? Would this be either equal to or greater than or equal to, 2 times 2 to the k plus 2 to the k? Could I make this replacement and claim that it's, greater than or equal to? It doesn't really matter. Let's do this greater. Okay. Would that be true? And if so, how do you know? You're going to look over here. So the smallest possible value k could be is 4. So this is 4, or some number that's bigger than 4. So if I take 4, or a number that's bigger than 4, and I replace nothing else, okay, but I replace that with a number that's smaller, this one will definitely be bigger than that one, right? Yeah. Okay, so this is because k is greater than or equal to 4. So I now know that k plus 1 factorial is greater than or equal to, well, this is just the same thing as our 2 to the k plus 1. Okay. And then I just want that by itself. So could I then replace this with 0 and have it still be true? Okay, so can I guarantee that 0 is smaller than 2 to the k? Certainly, because again, k, okay, is still greater than or equal to 4. So this is 16 or bigger. So if I replace it with 0, then this one is definitely bigger than that one. Okay. And that's exactly what I set out to prove, is that k plus 1 factorial is indeed greater than or equal to 2 to the k plus 1. Okay. And so I've shown it's true for 4. I show that if it's true for any arbitrary k, and it's true for k plus 1, remember what that means. That means that if it's true for 4, this tells me it has to be true for 5. And then this tells me that if it's true for 5, it has to be true for 6. And then this tells me that if it's true for 6, it has to be true for 7. And on and on and on it goes, right? So this starts the chain reaction, and this gets all of them. Without this, we would have nothing. This is very important. Okay. But you put those two things together, and we can say, therefore, by the principle of mathematical induction, okay, the n factorial will be greater than 2 to the n for all values of n greater than or equal to 4. Now this says nothing about when n is 3 or 2. It's only from the base case on. So our last section in chapter, well, sorry, were there any questions on that one? That one's a little bit easier to understand than the previous one, I think. Plus, you already thought of it. But were there any questions on that one before I go on? I think this one's easier to understand. All right, good. Okay, so the last section is just some other types of inductive proofs. So we've done mostly summations. But we'll also see a lot of inductive proofs, so we can use them with other kinds of things. Divisibility, recurrence relations, you see them quite a bit in there. Closed forms for arithmetic and geometric sequences, again, because these are summations, and but we can even apply them to set operators, logical operators, and my personal favorite, graph theory. So we're going to do a problem from graph theory. Okay. All right, so we'll just do a smattering of examples of different kinds of ways that you can use induction. All right, so we want to show that for any positive integer n, that 4 divides 3 to the 2n minus 1. Okay. There's probably other, like you might be able to do this with a direct proof. Okay, I don't care. We're doing it as an induction because we're practicing induction. Okay, so we use induction on n. Okay, so our base case. So what would our base case be for this one? 1, right. So if we're talking about positive integers, the very first positive integer is 1. So that would be our base case. So, you know, it's not written out that. You kind of got to read between the lines there. But yes, our base case is n equals 1 because that's the smallest positive integer that there is. Okay, so we want to look at what 3 to the 2n minus 1 is. So if we substitute, that's going to be 2 times 1 minus 1. That's 9 minus 1, which is 8. Okay, so since 4 divides 8, okay, it's true for the base case of n equals 1. Okay. So that establishes it for our base case. And we need to do our inductive step. Okay. So we're going to assume that 4 divides 3 to the 2k minus 1 for some integer k, some positive integer k. And then what we needed to show that if I replace k with k plus 1 in this expression, it'll still be true, right? So we need to show that 4 divides 3 to the 2 times k plus 1 minus 1. All right, so first of all, we have this 4 divides 3 to the 2k minus 1. Okay. So let's think about the definition of divides and what that would mean. Okay, so by the definition of divides, okay, so what would we get from that? What's the definition for 4 divides some value? What does that mean? Yeah, what is it?
It means that 4 goes into the value without a remainder.
Yeah, that means that 4 would go into this value without a remainder, which basically tells us that I could take 4, multiply it by some integer, and that product would be this number, right? So remember, that's the definition. So by the definition, there is an integer, let's call it A, such that if I took 3 to the 2k and subtracted 1 from it, okay, that would be 4 times A. Okay. So basically, if I take, and divide both sides by 4, I know when I do 3 to the 2k minus 1, the result is going to be an integer, A. Okay. That's what divides means. Okay, good. All right, so I know that. Okay, and so now I want to think about basically, I want to look at this value right here and see if I can write it as some integer multiple of 4 as well. So I need to consider this expression right here. So let's consider 3 to the 2 times k plus 1 minus 1. Okay, so let me distribute that through. This is 3 to the 2k plus 2 minus 1. And now I think, back, okay, I know that I'm going to have to get this inductive hypothesis into the game somehow. And this has a 3 to the 2k in it. Okay, this one right now has a 3 to the 2k plus 2. So how could I write at least this part of it so that it just has a 3 to the 2k, so it looks a little bit more like this? Okay. So how can I write this part as 3 to the 2k, so in terms of 3 to the 2k? Yep.
3 to the 2k times 9.
Yeah. So then this is really 9 times 3 to the 2k. Okay, and then we have this minus 1 over here. Okay. So I have a 3 to the 2k. Okay. I don't have 3 to the 2k minus 1, which is what I know something about. Okay. And I can't just group these together and replace this because this 9 is multiplied by it. So what I would really like, okay, I need somehow to get this 3 to the 2k minus 1. Okay. And so this is where, again, you can use a little bit of ingenuity. Okay, so I'm going to take this 9 times 3 to the 2k. Okay, and say, all right, well, if I replace this, if I were to put a minus 9 there, then I could factor out this common 9. And if I factored out that common 9, this part of it would be 3 to the 2k minus 1. Woohoo! That's what I want. But I can't just go subtracting 9 from an equation and expect it to still be equal. But if I subtract 9 and then add 9, I've just added 0. Okay? And so nothing has changed. Okay? And then my minus 1. So these two things are still equal. There's my 9 times 3 to the 2k. There's my minus 1, and I've just added 0 to it. Okay. But when I added 0 to it, I did that in such a way to help me get something that uses my inductive hypothesis. So I can just group these first two together, factor out this 9, and I'll have 9 times 3 to the 2k minus 1. I love that because I know something about that. Okay. And then the rest of this just gives me 8. So now that I have this 3 to the 2k minus 1, I can use my inductive hypothesis and say, well, 3 to the 2k minus 1, I can just replace that with 4a. So I'm going to take that and just replace that with 4a. And there's my inductive hypothesis. Okay. And so remember, our whole goal was to try to show that we could take this and write it as 4 times some integer. So now the question is, can I write this thing as 4 times something? Okay. What would I have to put in those parentheses? Yep, Vaughn.
9a.
9a would give me that part. What about this part?
Plus 8.
Plus,
Okay, not plus 8.
because I've got to distribute it too. So 4 times 9a will give you that part, and then I got to distribute it to this one to get the 8. Plus 2, right? Plus 2. Okay. And so, the last step we got to do now is just show that this is indeed an integer. Then I would have 4 times some integer is this, so it has to be divisible by 4. Okay. So, can I guarantee that this is an integer? Hopefully we've seen this in the past.
Yeah.
Yeah, so since the set of integers is closed under multiplication, which is what's happening here, and addition, which is what's happening here, okay, we know that that 9a plus 2 has to be an integer. Okay, so by definition, 3 to the 2k plus 1 minus 1, or sorry, 4 divides it. 4 divides that 3 to the 2k plus 1 minus 1. That's what we set out to show. And we can say, therefore, by the principle of mathematical induction, 4 has to divide 3 to the 2n minus 1 for all values of n greater than or equal to 1. Or I could have said positive integer, assuming n is an integer. I think that this one might take us more than, if it only took us 5 minutes, I'd be okay with it, but I think it might. All right, I think we're just going to stop here. We'll do our last couple next time before we start chapter 5. Okay. Okay, just to make sure you guys have enough time to finish up your quiz.
Fly, you fools.